Good afternoon, everyone. I'm coming here today to correct a mistake that I made in teaching reaction rates, and specifically the reaction rate for intermediates. I apologize that I made this error. It was all my fault, and that sucks. But let's get it fixed right before the exam here. What I told you was in a multi-step reaction that the slowest step of those steps is the rate determining step, and that your rate law is based on that part of the reaction only, that step of the reaction only. That is true. But then what I told you is that you could ignore the rates or the intermediates in that step and base your rate law on just the non-intermediates in that step, and that's not true. You do have to account for the concentration of the intermediates, and it's a small twist, but an important one to get the rate law. So I thought maybe I'd show you an example of what this means. So right now I have this fictitious reaction that happens in these three steps. This isn't a real reaction, but I wanted to just kind of show you the idea of it using this reaction. The logic works out for all of them. So on the first thing we do is we notice that we have three steps. We have a fast, a slow, and a fast. So this is the rate determining step. Our rate will be based on this step. And our rate is dependent on only the reactants. Now before I told you, because this is an intermediate, it's made here then consumed, that you could totally ignore the existence of this one and just focus on this one. So I would have told you that the rate law, the rate is equal to some constant K times the concentration of NO, and you'd be done. That's actually not true. We have to account for oxygen. So here I'm going to put in and the concentration of these oxygen atoms. Now the problem is there's no hope of us ever measuring a concentration of an intermediate because it's made and consumed too fast to get that. But we can go back here and see in this reaction when it was made. We say, okay, it's made here. There's going to be some equilibrium set up in this reaction, and its equilibrium constant is equal to some value, K, is equal to the products divided by the reactants. In this case, the concentration of O, and because it's raised, it's 2O, it's squared, raised to the second power, divided by the concentration of O2. Now the reason we went for this equation for the first reaction is we need some way to express the concentration of O, oxygen atoms, in terms of a reactant that we can actually measure the concentration of, in this case, O2. All right, so now if I solve this for O, I multiply both sides by the concentration of O2, and I get that the concentration of O squared is equal to K times the concentration of O2. And because I'm looking for just the concentration of O, not squared, I'm going to take the square root of both sides. So I'm going to square root this, and then I'm going to take this to the half power, which is the same as square root. Now I have an equation that tells me the concentration of oxygen atoms, this O, in terms of the concentration of oxygen, which is an actual reactant that I can measure the concentration of. So now what I do is I take this and I plug it in right there to get rid of that in my rate law. So my rate law is equal to some constant K times the concentration of NO. And instead of putting a concentration of O, I'm going to put all of this mess in. So the square root of K times the concentration of O2 to the 1/2 power. Now, these two constants are just constants, so we're going to make them into a new K. Right? We don't know what the value of that is anyway, so it's going to be some value K times the concentration of NO times the concentration of NO2 to the 1/2 power. And that's where that second component comes in. So O2 is important in the rate, but only in the sense that it makes this, which is how the 1/2 power gets filtered in over time. So I hope that helped with the process. So the overall process is you write out the rate law for the slow step. Then if you have an intermediate in there, you have to go back to the equation where the intermediate was made, almost always the previous equation. Set up the equilibrium constant for that equation, solve for the intermediate concentration, and then substitute in that equation into your rate law and combine K's into 1K. So at this point, all I can do is apologize for making the mistake of telling you guys that wrong, and hope the best that you guys most of you get to watch it and kind of see how to do this process. If you have questions, I will be paying attention to Schoology, and I will be here this Saturday for extra help as well. All right, have a nice day, my friends.